Did your exam go? Right. Let's get down to probability now. So let us start from basics. Like in how many ways can you find the probability of an event? So suppose you want the probability of an event. We can say it is 0 if A is impossible, right? So this is something that is very basic. Or if A is nothing but the null set. And similarly, P of A will be 1 if A is a sure event, or if your A is the entire sample space. So these are very, very primitive ideas. Apart from this, we have certain ways of finding out probability of A, right? So what are the other ways of finding the probability of any event? So I can find probability of A using probably the total probability theorem. I hope all of you know this, right? All of you know this theorem, right? Recall this total probability theorem, addition theorem probability, which you learned in 11th standard. P of A union B is P of A plus P of B minus P of A intersection B. So I will have P of A to be sum of these two minus P of B, right? This is another way of describing your P of A. There are various ways of finding out P of A, right? This is one of them. Is there any other way that you can think of for finding P of A? Of course, we know many concepts, but I'm just recalling certain things. Can anyone think of any way of expressing P of A other than these?
Uh, 1 minus P of A dash.
Yeah, exactly. I like this, Ishan. Very good. Yeah. 1 minus the non-occurrence. It's a very important aspect because A and A bar are always exhaustive. Okay. If you add the probability of the occurrence and probability of non-occurrence, it will always add up to 1. So I like this answer. So apart from this, is there any other way of expressing P of? I can think of one more thing. See if you are okay with it. Okay. Can you guess? Can you guess what I'm writing in the denominator? Anyone?
P of P bar A.
Very good. Very good, Sukidra. I was waiting for this. Yeah, this is actually from this idea. No, P of A intersection B is given by P of A into P of B given A. I hope all of you are aware of this. From this only I'm getting that. Okay. So P of A is a part of that. Okay. This is called multiplication theorem, right? Just like we have addition theorem of probability. I'm just making you recall all the fundamental theorems that will be useful in various situations. So this is, if P of A can be got from addition theorem, it can be got from multiplication as well. Okay, so this is one way of looking at it. Is there any other way of expressing P of A? Of course, this also arises from, it will also make you recall the conditional probability idea. No, from there also it is possible for me to get the value for P of A. I can say I got P of A either from here or from here. Okay. Both these are actually valid. Okay, for getting P of A, I could have used anything. But you know what? Both these are same things. No? They are one and the same. But one is known as multiplication theorem. Other one is known as the definition of conditional probability. But both are one and the same. If we shuffle what is there in the second, we get the first. If we adjust the first, we get the definition of the conditional probability. So they arise from one and the same concept. So P of A can be got from any one of these. But apart from this, there is something very important from which P of A can be got. Let me see who recalls that.
P of not A intersection B.
Yeah, not A.
Actually, sorry. A intersection not B.
A intersection not B.
Plus A intersection B.
Very good. Yeah, excellent. Yeah, that's because A is actually the union of these two disjoints. I was not hoping for this anyway, but she came across something very brilliant. So let me add that also. I hope you understand what she said. What she said was A has two disjoint sets whose union is that. No, for example, I can say A is the union of this and this. So she said, let me write that as sum of these two disjoint sets. So that's what she has done. Okay, that's a brilliant idea. Yeah, to think of A as the union of these two disjoint sets. And if you can express any set as the union of two disjoint sets, you shouldn't hesitate to write its probability as sum of their individual probabilities, because disjoint sets signify mutually exclusive events. No? Disjoint sets always signify mutually exclusive events, and therefore the probability of their intersection will be 0. And therefore, the probability of any event, which is the union of two disjoint sets, will be simply the sum of their probabilities. So it stems from that. I perfectly agree. But I was looking for something else. Okay, let me see who's going to tell me that. I'm waiting for some brilliant student to recall this, which is actually very useful in many contexts. So let me see who among my students is the most brilliant. Okay, I'll help you. I'll give you a clue. Okay, I'll give you a clue. This is my universal set. And A seems to be a part of that universal set, but it has got something to do with those three mutually exclusive and exhaustive sets B1, B2, B3. A intersects all of them. Okay. And just think of what Aparna said just now. And I think your answer is ready. In the sense, your A can be thought of as the union of, she gave a simple example of how a set can be expressed as the sum of mutually disjoint sets, right? That way, she had 2 sets to unify, but I'm having 3 sets to unify. So what can be my A in this context? Of course, here A is, can someone attempt this? In this case, what will be P of A? In the previous case, it was the green portion plus the pink portion. But now it will be, can you think of these portions? What are these actually? What is that green portion?
P of A by B1.
It is green portion. Isha, green is occurring in A as well as B1, right? Isn't the first gate B1 is the B1 set, right? What I'm striking, that is your B1. And A seems to be there, part of A seems to be there. And your green portion is nothing but the intersection of A with B1. How do you see? How do you depict it?
Is it
Hmm.
B1
You
B1
got it.
intersection A?
Very good. You got it. A intersection B1. Yeah. It is A intersection B1, that green one. Okay. What is the pink portion? The pink portion seems to be A intersection B2, correct? Pink portion is A intersection B2. And of course, the yellow portion, what I've shaded finally, is this. So this idea is very much useful when A is not something that's plain, but it has got caught, inside a portion which is common to 3 other sets, which happen to span your universal set. So this is invariably the situation which is given to you, wherein we are, supposed to use the total probability. And therefore, your P of A will be the probability of these, the union of these disjoint sets. So what will be the characteristic of the union of disjoint sets? Just now we have seen if Y and Z are disjoint, then what happens is that the probability of their union happens to be sum of their probability, right? The same thing applies here. So it will be P of A given B1 plus P of A given B2, A intersection B2 plus P of A intersection B3. Okay. How did union become plus? Or why did union become plus? Because all these shaded sets, green set, pink set, and yellow set, they're all disjoint. Okay, and therefore union became plus. Okay, how do I deal with the intersection now? Which comes to my rescue as far as the intersection goes? Whenever we are supposed to find out the probability of the intersection, which theorem comes to your mind immediately? Which one?
Conditional probability.
Very good. Yeah, the multiplication theorem, which I was mentioning earlier. Do you remember? I was telling you about the very important, okay, multiplication theorem, which allows you to express the probability of the intersection as conditional probability of one into the unconditional probability of the other. That's what the multiplication theorem says. So would someone like to express this using the multiplication theorem? How can I write it?
P of B1,
P of
B1,
very good. P of B1 into
P of A bar B1.
very good. Yeah. Look at the way she has intelligently constructed P of A given B1. She could have said P of A into P of B1 given A, but she didn't say that. Why? There are two ways of expressing, no? But she didn't choose the other way because this is what we are finding out. So it would be foolish on our part to write P of A on the right. So she chose to write P of B1 on the right, which is commonsensically correct. Okay, what is the next one? Similarly, it will be better for us to use, right? Yeah, I'll call you a bit later. Okay. P of B3 into P of A given B3. And this is such an important aspect of probability. Does anyone remember what this idea is known as? We have used it very frequently and it is supposed to be important. Can someone tell me what this idea is based on? What is
Bayes theorem.
Bayes theorem? What is this called?
Is it related to Bayes theorem?
Yeah, it is somewhat Bayes theorem, but it's not the entire Bayes theorem, no, Sai.
Total probability.
Very good. Very good, Shah. This is called total probability, which comes to a rescue in many situations. And therefore, I wanted to start with that. But it starts from the idea of finding out the probability of an individual event, but in various situations. But here, the probability of that event is intertwined with three mutually disjoint sets, which happen to be spanning the sample space. So what do I mean by spanning the sample space? What is that actually giving us? It is a situation in which the union of three sets is actually a universal set, and those sets are individually or pairwise disjoint. Okay, pairwise they are disjoint and their union brings about the universal set. So this is called the total probability theorem. So in such situations only, we use the total probability theorem. Okay, there is another important aspect where we need to know certain terminologies. This is simply about probability of an event, which we dealt with, and we came across so many things, while discussing about the probability of an event. We came across the total probability theorem. We came across multiplication theorem. We also came across addition theorem. All important concepts were recalled while we were simply discussing the probability of an event. But there are certain other important terminologies which we need to know in like intersection P. It has got so many, varieties of expression. So like, for example, I'm interested in this event. Okay, A and B seem to be two different events. What does A intersection B depict? Can someone answer? A and B are two individual events. What does A intersection B depict, or what does it stand for? Say A is the occurrence of A. Capital A stands for occurrence of A, and capital B stands for occurrence of B. Okay, what does A intersection B stand for? What is it? It is the occurrence of
Both the events.
very good, A and B. Okay, so that's what we need to know. Intersection always stands for and. Okay, and this probability, therefore it is an event, right? It is also an event, so its probability can be thought about. So in how many ways can I express P of A intersection P? So this is another interesting question, just like how we had experience with P of A. It was a separate event, right? It was a single event, single set. But we have now two sets, found at the intersection found between two sets, and another event is created. What is the probability of that event? That's what we are interested in finding out. So suppose this probability is asked where A and B are any two events. I simply don't know the nature of the events of A and B. I don't know whatsoever the nature of A and B. In that case, how do I express P of A intersection? What comes to your mind immediately?
So P of A plus P of B minus P of A union B.
Very good. Yeah, this is the best way. This is the best way to begin with. Okay, because this is such a universal result and it can't fail because it works for all A and B. That is the idea. Okay, because it arises from which theorem? The total probability theorem. Okay, which is such a sure short idea, isn't it? It works for any two events, irrespective of whether they are mutually exclusive, whether they are independent. Nothing needs to be investigated because this is valid for any two events. If A and B are any two events, okay, this will be always true. So this can always come to your rescue. And of course, the individual ideas, of course, we can make use of later on, whether they are mutually exclusive or mutually independent. All those things can be made up later on. But this is so important, vital. Okay. So this is one way of expressing P of A intersection B. Is there any other way that comes to your mind? Very good. Yeah. If you can think of addition theorem, you can also think of multiplication theorem, isn't it? So what does the multiplication theorem say? It says it is the unconditional probability of one into the conditional probability of the other. Okay. Or the multiplication theorem also gives you the liberty to choose the conditional probability and unconditional probability. You can swap, right? So whichever applies to that situation, you can take it up. So this is arising from, this is backed by what? Multiplication theorem, right? Multiplication theorem is again, works well for any two events, because in case they're going to be independent, this conditional will become unconditional. So it is valid for everything. So is there any other way of expressing P of A intersection? What if they are mutually exclusive?
P of A into P of B.
Ishan, very good. Yeah. But that is if they are independent, no, not when they are mutually exclusive. If they are independent, okay? Yeah, you gave me one of the possibilities, but this works only if they are independent, okay? I still wanted to answer one more. What will be this if they are mutually exclusive? If they are mutually exclusive, when will they be mutually exclusive? When they are mutually exclusive, their intersection will be
0.
very good. Very good, Anirudh. It will be 0. P of A intersection B will be 0 if they are mutually exclusive, right? That possibility again exists, right? Because independence and mutually exclusiveness, they are different characteristics altogether. One doesn't imply the other, right? They are independent attributes. And therefore, we should investigate separately only. If they are independent, it will be the product of their probabilities. If they are mutually exclusive, the probability will be 0. Is there any other way of expressing P of A intersection B? Let me see. Because many of you are very creative, so.
One minus P of A dash, your intersection B dash.
Ah, Sai. Excellent, Sai. Did you say this or did you say, because I couldn't hear you towards the end. Did you say this? This is what you said?
Wait, I told intersection.
It should be union, right?
It's union.
Okay, so it should be the union. Yeah. This is backed by human consent. One of the De Morgan's. So this is the all about intersection. Okay, let us pass on to union now. If A and B are any two events, what does A union B depict? Let us understand what does A union B depict. A union B stands for anyone?
Or B.
Huh?
A or B.
Very good. A or B. But the thing is, when we say or in logic, okay, or in probability, it also includes this. I suppose all of you know this. It's a very tricky thing. Okay? Many of us think that or means exclusive or, but it's an inclusive or in set theory because union, all of you think of union. Which is union? Can I shade and show you? Union. Union depicts this portion, right? Think of the portions that it comprises. It has this portion. Okay. What is this portion? Both. Both is there in union, right? So A union B is A or B or both. That is also there, right? So what is your P of A union B? While finding out P of A union B, what are the ways in which you will be approaching this? What is P of A union B to begin with? What is the first choice for you? Popular choice. What is it? P of A plus P of B minus P of A intersection. Wanted to tell you one more. Okay, I don't know how many of you are aware. Of course, this depicts this, but there is one more important terminology associated with union. Does anyone recall? A or B or both, or there is one more terminology which can be associated with union. Just like here, intersection means what? Occurrence of the simultaneous occurrence of A and B, right? Union means A or B, right? But there is one more that is possible. It's very popularly used in problems also. Let's see how many of you recall. They don't ask you like this, no, find the probability of A or B or both. And that's not the way they pose the problem. They ask you something else, right? Let me see who recalls. It's a very important terminology. I don't know why you forgot. Are you giving up?
Is it one?
One of them?
No, like one.
No, it's at least one. Okay, at least one of them. That is what is depicting A union B. Mark this as important. Don't forget it. A union, at least one means A union B. If there are three events involved and they're asking at least one, then it depicts A union B union C. Understood? At least one always depicts the union of the relevant sets. So remember this terminology. Intersection means A and B. Union means at least one. Okay. One more way of depicting A union. Let me see. Is there any other way of writing A union B? This is backed by addition theorem. No, we are all quite familiar with this. We are all fond of this, and it's used very frequently because it is valid for any two events. That's why. Okay, is there any other way of writing A union B? Of course, there are many corollaries of this addition theorem. So we can think of all those. P of A plus P of B minus 0 if, can you complete?
Mutually exclusive.
Very good. Very good, Anirudh. If they are mutually exclusive, your addition theorem turns out to be this, right? We can have one more corollary. It is equal to P of A plus P of B minus, you would have guessed what I am about to do.
P of A into P of B.
Independent. If they are independent, the same theorem becomes this, another corollary of that. Okay. So it has got various forms. Of course, this is the parent form, but it can, you know, give rise to various forms depending upon the kind of events that you come across. It is A intersection B will be 0 if they are mutually exclusive, and it will be P of A into P of B if they are independent, right? Okay. Is there any other way of expressing P of A?
1 minus P of A
very good.
will be the whole.
I know you're capable of saying this. 1 minus, come on. What is it?
A union B the whole dash.
Very good. What is it?
A dash intersection B dash.
A bar intersection B bar. Sai, you understand? If it is union here, it has to be intersection here. That is when De Morgan's law.
Yes, ma'am.
This is De Morgan's. And this way is very elegant in many cases, especially when you are dealing with what? The union of three sets, for example. That is when this idea will be extremely useful because we don't have to deal with addition theorem for three events, which can be tedious, which can be cumbersome. But this will be very elegant because all you need to think of as the complement of intersection of the complements. Okay. So the probability of union of several sets is nothing but 1 minus the probability of intersection of their complements. Okay. So this also arises from De Morgan's. This will be very useful for finding out probability of at least one. Okay. Let us now turn our attention to A intersection B bar. Can someone tell me what is the terminology for this? A
1
intersection,
minus
occurrence of,
A but not B.
very good, occurrence of A and not B. A and not B. A and not B. Okay. So can I elaborate that? What do I mean by saying occurrence of A and not B? That means what? I give the problem to A and B. A solved it, but B failed to solve it. Who solved it? Who solved it? Only A. Understood? Occurrence of only A. So when this only A has got an implication, right? I gave the problem to 2, but I'm saying, I'm complaining to you all, saying that I gave to 2, but only A solved it. So what do I imply then?
P
A
of
solved
A.
it. B didn't solve it. That's what I'm implying, no? There is an implication in that statement. So it's a very subtle way of saying, okay, occurrence of only A means B failed to solve it. That is hidden there, Okay. Who's going to give me expressions for finding the probability of this event? I want A intersection B bar. Universally, for anything, any event that I want, I actually can use what? The Venn diagram. I'm very fond of this Venn diagram because it will tell me exactly where I am, which area I'm looking at. Okay. If the entire area is 1, if the entire sample space fetches me the probability of 1, What is this area that I'm looking at? This is what is A intersection B bar, right? You all agree? This is
A minus A intersection B.
Very good, Jessica. Yeah, just put it as probability. So we can see that this yellow area that I've shaded is not the entire A. From A, I need to subtract A intersection B, then I get this. Yeah, that's a brilliant answer. This is something that's universal, so I will always use Venn diagram whenever I need to find out the probability of something. This will work sure shot for me, so I will use that. Okay. Is there any other way of finding out P of A intersection? I think we took P of A intersection B bar. What did we take? P of A intersection B bar. Oh, yeah. Okay, that's some space. A intersection B bar, right? Let me go to the top. P of A intersection B bar. This is what I want, right? Okay, can someone give me one more expression? Of course, I can use Venn diagram and find this. Apart from this, is there any other way of finding?
P of A union B minus P of B.
P of
A union B minus P of B.
Very good. I like this answer also. Who said that? Vinay, Krish, brilliant boy. Look at his answer. He says from A union B, if I subtract B, I'll get this, right? Yeah, sure. Any other way of looking at it?
P of A into 1 minus P of
Very
B
good.
bar.
Yeah. See. Yeah, that possibility exists, but only if A and B are independent. Okay. If that information is given to me, or if I come to know about it, or if I explore and find out that they are independent, that is when I can break it as a product. So intersection won't become a product by default every time, right? So we may have to use Venn diagram only, the way Krish used or the way I used earlier on, so those things. But if we come to know certain additional details, then we can. Is there any other way? I'm just interested in finding out if we can think of any other way of finding out this.
From P of A bar B into P of B bar.
Very good. Who said that? Subhitra. Excellent. She is using what? She is using very multiplication theorem. She used it in one way. Of course, we can also use it in some other way, depending upon what we are looking at. Okay, right? I can write this as P of P bar given A into P of A. So that choice is with me. Depending on what is available in the data, I can use various forms of that. Okay. Still, you are not given me what I am looking at. One more I want. You know
We
what?
can use De Morgan's law.
We can use it. That's what I'm thinking. Come on, when I say that. Kibi?
P of A complement union B.
1 minus that. 1 minus
Yeah,
P
sorry, 1 minus.
A bar union B. Another way of expressing. This is, De Morgan's law is always, again, universal. No, can be used in situations where it is tough. Okay. Let us pass on to the next possibility. Of course, I can also talk about A bar intersection P. That will be similar to this. Treatment will be similar to this. So I'll try to alter it by another event like this. How about this? Can someone tell me the terminology of this? What does it depict? Can someone first tell me what this was, as discussed in the earlier case?
Only A.
The Okay, this is only A. And what is this?
Only B.
B. What is this?
Union.
English.
I
In
mean, both. Either this or
Only A or only B. Okay, literally translated, it means only or only A or only B. But we want more sophisticated terminology. So what can it be? An equivalence of this. What can it be? Only A or only B. Of course, that's what it means literally.
Exactly A or B.
Ah, very good, Nishant. Bright boy. Exactly one of them. Okay, it's called exactly one of them. So how about its probability? A intersection B bar union A bar intersection B. But we know whenever we seem to have something to be found, we always go to our Venn diagram, because this Venn diagram is such a universal thing. Okay, we can use this in all cases, in all possibilities. Whenever A and B are any two events, we are free to use this. So which are the things that I'm looking at? What are the pieces? What is this piece? This piece is this inside A, outside B piece. Okay. What is this piece? What is this piece? This piece is this, right? Inside B, outside A, that piece. So I'm looking at unifying these pieces. But these pieces are what actually? What I've depicted using red and white. Are they disjoint? Are they disjoint or not? Are they separate or not? That's what I'm asking.
P of A union B.
Right. They are separate. That means these are technically, what are they? They are mutually exclusive, right? They're technically mutually exclusive. They are mutually exclusive. So how about their union? We have already seen when we are finding out the union of two disjoint sets, it is simply sum of
their
their
sum.
Yeah, exactly. It will be their sum, because these two are disjoint. Set wise they are disjoint. Event wise they are mutually exclusive. The sets are disjoint. The events are mutually exclusive. So both mean the same, right? Whenever sets are disjoint, we understand the corresponding events to be mutually exclusive. That means there is no possibility for them to happen together. Okay, that's what it depicts. So what is it further? We have analyzed this already, and we know that this is nothing but only A. So that can be P of A minus P of A intersection B. And this is nothing but inside B, and therefore it has to be P of B minus P of A intersection B. So only A means it prevents B from happening simultaneously, no? So from its portion, we are subtracting A intersection B. So that's what I understand. And only B means it's not P of B. I have to eliminate A happening along with B. So I'm subtracting A intersection B. So that's happening here. Only B, it's happening. Only A, this is happening. So what is the total of these probabilities? It's nothing but P of A plus P of B minus 2 times P of A intersection. Okay. So the probability of exactly one of them. Okay, that's what actually it depicts, right? That's what it stands for, right? So the probability of exactly one is P of A plus P of B minus twice P of A intersection B. It almost looks like your addition theorem, but it's not. No, there is a subtle difference. Addition theorem talks about probability of at least one, right? Probability of at least one, and it tells you that it is the sum of their probabilities minus the probability of their simultaneous occurrence. So what is the difference between these two? The probability exactly one has got 2 accompanying P of A intersection. That's the subtle difference. So if it is at least 1, it is merely P of A intersection B that gets subtracted. If it is exactly 1, it is twice P of A intersection B that gets subtracted. So that's the difference between these two. So this is known as addition theorem. So this is as a different context. Okay, we have exactly one situation here. P of A plus P of B minus 2 times P of A intersection B. So these are the terminologies that you've got to get used to in the concept of independence. Another important aspect of independence is that, okay, independence is your second topic, isn't it? First topic being your conditional probability. From there only the idea of independence comes. Actually, recall that conditional probabilities are defined this way, right? P of A intersection B by P of B. This is what the conditional probability says. But what happens is that there's a conventional way of finding out the conditional probability. But if the events are independent, for example, if there are two students who don't copy from each other, okay, who don't copy from each other, then occurrence of B when already happens. For example, B has already happened, or B has already solved a problem. Okay, then what is the probability for A to happen? Or what is the probability for A to happen? That's what we are finding out. No? What is this probability? Probability of A to happen when B has already happened. Okay, that is what is known as P of A slash B. What comes after slash has already happened. But suppose A is very independent fellow, it doesn't look at B at all. Then the probability of A solving the problem will remain intact. No, it wouldn't be affected by whether B has solved it or B has not solved, because he's not looking at him. So he is not even aware whether he has solved it or not. So the probability of A solving it remains intact. Say, for example, there is a 75% chance that A solves it every time. He's not solving it 100% of the times, but 75% times he is solving it. But when B sits next to him, he solves it, say, 90% of the times, then I become suspicious, no? Then I think that, oh, A and B are dependent, or A depends on B to do things, okay? So that means this is an important aspect of independence. So A and B are independent if and only if when the conditional probability and unconditional probabilities happen to be same. So this is the basic idea of independence. Is the basic idea of independence. So according to that, when it is independent, what will happen? When A and B are independent, if and when A and B are independent, what will happen? The chance of A solving it when B has already solved, or his individual probability, both will remain the same, right? But according to the definition of conditional probability, the right-hand side remains, right? So call this as 1. When they are independent, 1 becomes, the left-hand side becomes P of A. So what happens is that a new concept of testing independence emerges. Of course, this is the basic idea of independence. But from 2, another concept of independence, totally different concept of independence arises. In a sense, I come to know that independence can also be tested this way, and I find it very convenient, and statisticians, also found this to be more, useful in detecting whether events are independent or otherwise. Okay, but the basic idea is this, right? Whenever A and B are independent, the unconditional probability and the conditional probability should remain the same for any one of them. This can also be this, even for B. P of B given A should be the same as P of B. That way also independence can be tested. But from both, what arises is the common idea of testing independence, or the universal way of testing independence emerges from this, which is P of A intersection B is P of A into P of B. Okay, this is the basic idea whenever they are independent. I hope all of you know this. Okay. But based on this, what they can ask you, certain theory questions are possible in this, or corollaries of this. The first one is, if A and B are independent, okay, they can ask you to show that, prove that A bar and B are also independent. Okay, this is one more derivation which they can ask you. Okay, mark this as important. It has come in the board exam also previously. So let us try this proof. If A and B are independent. Okay, always remember, if there is a statement and if there is the terminology if, that means what? What follows if is given. Okay, that's given to you. If A and B are independent, that means I am given A and B are independent. And what is to be proved will always follow this, right? Prove that. What should I prove? To prove that, I should prove that A bar and B are independent. So this is my task. My task is what? To use the fact that A and B are independent. I should try and prove that A bar and B are independent. Okay, let me understand what this actually means. Let me understand it fully, the implication of A and B being independent. What is your take? When are they independent? Which criterion are you going to take? That one. That is only popular, isn't it? Whenever two events are independent, this is only to be assumed. So I'll take this to be P of A intersection B is equal to P of A into P of B. Let me assume that this is given to me in all contexts. And I have to try and prove that, that is to prove that, it doesn't imply. I have to try and prove, that is to prove that. I'm just trying to bring more clarity in this. I want to prove A bar intersection B is equal to P of A bar into P of B. That's what I'm trying to prove. Okay. What is the best way of proving something? I want to prove something. Call this as 2. Call this as 1. So I have to try and prove 2. Okay. In the process of proving 2, at some point in time, I may have to use equation 1. That comes much later. But in order to prove 2, what is my approach? I will take LHS of 2 first, and I'll try and prove it to be RHS, right? That's the best way of proving. So this is nothing but P of A bar intersection, which is, what did I tell you? Whenever I have to find the probability of any unknown event, okay? What is my best way of finding out? Venn diagram. Venn diagram. Okay, A bar intersection B. Where will it be? Who's going to tell me? Where is A bar intersection B? A bar means what? Outside A. B means inside B. So which one will you be? This one you'll be shading. Okay, what is it in Venn diagram? What is this portion in Venn diagram?
P of B minus P of
From B, I have to subtract A intersection B. And A intersection B and A bar intersection B are mutually exclusive, and therefore P of B can be expressed as sum of these two. And therefore P of A bar intersection B will be just this, P of B minus this. Yeah, you are very correct. And in the next step, can I make use of what is given? This is given to me, right? I'm given this. So I have to make use of it. Okay. And this is the right time to make use of it. And within brackets, I will write given. Okay, that's given to me. Now I'm using what is given. Because they are given that they are given to be independent, I'm making use of it. What comes out in the next step? What is common between these two terms?
P of B.
P of B is common. So I'm taking it out. What is coming? The first term, 1 is coming.
1 minus P of A.
Minus P of A is coming. What is 1 minus P of A? The complement of A. That's nothing but A bar. Okay. So did I come across the the right-hand side now, the right-hand side of 2. I took the LHS of 2 and in the process, I've come across the RHS of 2. So is 2 proved? Yeah, hence. So we have proved 2. This is one of the possible theory questions that you can have regarding independence. And another thing is, they may also ask you this corollary, another corollary. If A and B are independent, if they are independent, prove that A bar and B bar are independent. Okay, this is another theoretical question that is possible. So let's see how the proof goes. Please go to the middle row. Okay, let's see how the proof goes. What is given? What did I tell you? What follows if is given, right? So we are given that A and B are independent. So again, that can only mean this. No, of course, it can mean various things, but popularly it means only this. So let us stick to this, call this as 1. And what should I prove? I am supposed to prove that both their complements are also independent. That means A bar and B bar are independent. So I'm bringing more clarity. I want to prove that probability of A bar intersection B bar is P of A bar into P of B bar. Call this as 2. In the proof, I'll be taking LHS of P of A bar intersection B bar. Okay, who's going to tell me what this is? Because there lies the important step forward.
1 minus P of A union.
Very good. Yeah, I like this. 1 minus P of A union. Yeah. Of course, we can also find this out from what? Your Venn diagram. A bar intersection B bar. Can someone tell me where will that portion lie? A bar, what is common to A bar and B bar? Where will it lie? Outside A and outside B. Which portion is that? Common to what is outside A and outside
Universal
B?
set.
This is the portion that we want. This is what I am painting in red. You know, that is actually your A bar intersection B bar. Outside A and outside B. That is the portion. So what can it be? It can only be the total minus the union, right? Okay. After that, what do I do? What do I do for the situations like this? That's why I was training you for writing P of A union B. How do I? Which one? What comes to your mind immediately? Yes, Nikita. What is it?
P of A plus P of B minus P of A union B.
A intersection.
Intersection.
Intersection. It comes from which theorem? Addition. Where? No. A and B are independent. I am yet to establish that A bar and B bar are independent. I can't use it right now. That's why this theorem enables you to use it in future. Once you establish it, any intersection can be interpreted as a product, but after proving it only. So right here, I can only make use of the independence between A and B. Nothing else can be made use of. Okay, so let me handle it this way. P of A plus P of B minus, this is nothing but P of A into P of B. That is actually 1 minus P of A. I am removing the brackets. I am removing all the brackets. After that, what I see is the scope to factorize by considering P of B to be common. Can you see P of B arising as common between the third and fourth terms, right? I can see that P of B is occurring common between the third and fourth terms. So I'm taking them out. But after doing so, I find that 1 minus P of A is common now, right? I can take out 1 minus P of A, this binomial term I'm taking out. So in the first term, I'm left with 1. And in the second term, I'm left with P of B. Can you see that? So we have come across the final step. Okay. This is nothing but P of A bar into P of B bar. And this is exactly what we wanted to prove. Okay. Hence prove that whenever A and B are independent, the independence of A bar and B bar is also guaranteed or assured. Okay. So we have proved it also authentically. We didn't make use of anything else apart from addition theorem, which is authentic, which works for every case. Hence, it is valid. Yeah, the proof is very much valid. So this is all about independence. And next aspect is your total probability theorem, isn't it? Total probability theorem. Of course, we recalled it in one context, but shall we recall it once again? The situation where the total probability theorem works. For example, suppose I want white balls from several bags. The probability of getting the white ball when there are several bags to choose from, the probability of the white ball will be probability of choosing the first bag and then choosing white from it. Okay. And then the probability of choosing bag 2 and then choosing white from it, or choosing bag 3 and choosing white from it. So these are the situations where your total probability theorem works. So for example, I have several bags, bag 1, bag 2, and bag 3. What I find is that all of them contain white ball, right? That means white is supposed to be a part of all these bags. You know, there is an event which is intertwined with all these things. No, but I want the probability of that one which is in focus. I want the probability of this particular event, but it has got everything to do or something to do with everything, right? It has got everything to do with all these B1, B2, B3. So the probability arises this way. Another way of looking at this is when you find out there are many factories, okay? Say, for example, F1, F2, F3, there are 3 factories, say, and all of them inevitably, they produce some defective items. So the defective items are part and parcel of F1, F2, F3. Some of their units are defective. What is the probability of finding any defective item? It is the probability of choosing the first factory and then getting defective from it, or the probability of choosing the second one and finding the defective from it, or choosing the third and then finding the defective from it. So this is how the total probability theorem goes. It is very important in context where you have, you know, a particular event in focus, but it has got something to do with the other events which happen to span your sample space. So this is your universal set, right? Universal set is nothing but your sample space. So your B1, B2, B3 seem to be exhaustive cases of that sample space. For example, say there is a town, okay? There is a town in which there are 3 factories. Okay, the items are produced only from these factories. That means these factories span the town. That means there is nothing else there. No other factories there. Only these 3 factories are there. That is the situation. Okay, that means this union of these factories is spanning your town, right? And D is a sub-event of that. So in context like this, where we use the total probability theorem is very useful. But Bayes theorem is actually extensively making use of the total probability theorem, but Bayes theorem seemingly addresses the conditional probability of seemingly impossible things. For example, I found out the defective item. Say I go to a shop and I found the defective item. Later on, I'm wondering, what is the probability that it might have come from F2? Okay, I strongly suspect that F2 is the culprit of this. Say I'm the inspector. Okay, I go to a shop and find out particular item to be defective, but I want the probability that it could have come from F2. This is a seemingly impossible, conditional probability. That is when we use Bayes theorem. Okay, you come across something, always I say, okay, I always tell my students, whenever you strongly suspect that Bayes theorem is what is in force in this particular problem, you go to the last line of the problem and jot down what is the conditional probability that he's talking about. If you can make out what is the conditional probability that he wants, the Bayes theorem is just the opposite of that. That's why it's called what? It is called the theorem of inverse cos. Okay. So this will be invariably your numerator in Bayes theorem. Whenever you come across a seemingly impossible conditional probability, that is when Bayes theorem comes into force. And what is there in the denominator? It will be the probability of the event that is coming after slash. That is P of D. And we know the probability of D can be obtained using what? The total probability theorem, isn't it? D given F2 into P of F2. And what is P of D? We know the situation, right? F1, F2, F3. And the D is a part of that. And therefore, your D is going to be P of F1 into P of D given F1. All possibilities. P of F2 into P of D given F2 plus P of F3 into P of D given F3. So, if you understand this structure of Bayes theorem, any problem can be solved. Okay, so you need to make out what conditional probability is that they are interested, find out that, and you write the reciprocal of that on the right side and multiply it by the probability of what occurs after slash. And in the denominator, keep on varying that, what occurs after the slash. We had, after the slash, we had F2 occurring, right? But we need to consider by shuffling what is happening in the denominator. That F2 is happening, no? We have to write it as F1, F2, F3. That is the structure of Bayes theorem. Okay. So if you have understood all this, then I think what lies later on, the only thing that you need to know after this is probability distribution. Probability distribution of a random variable and the mean of a random variable. These are the things. Okay? And mean of a random variable. This is the last aspect of probability. Okay, who knows what is meant by a random variable? We always say, no, we choose a notation for the random variable and then say, let X stand for the random variable, depicting the number of balls or depicting the number of cards drawn or depicting the higher number, whatever they ask for, they will ask, in the question, they will ask, find the probability distribution of the coins, number of heads, or they'll say, find the probability distribution of number of red balls. Based on that, we'll name your capital X. Remember, capital X stand for a random variable usually, but what does random variable denote? What does the terminology mean to you? Random variable means, what is the job of the random variable? What does it do? Your random variable does something very important. What it does is that a random variable assigns a numerical value. Okay, it assigns a numerical value to the events of the sample space. This is its major job. Okay, you're doing some experiment. Okay, and there are outcomes in it. What it does is that there is an important job done by the random variable. What it does is that it groups many possible events and then assigns a numerical value to it. It's a very simple idea. No, the idea of the random variable is very simple, but it has got far-reaching implications. Okay, let us see how it actually works. Suppose if you're tossing 3 coins. Okay, if you're tossing 3 coins. What is my sample space? I know the sample space will have how many possibilities? We are tossing 3 coins, right? From each of them, 2. 2 into 2 into 2, 8. So HH, HT, TH, TT. Then again, replicate HH, HT, TH, TT. Put H in the first place for 4 of them. Put tail in the first place for 4 of them. Then you would have created your sample space, right? I want to allocate some random variable to this experiment. So I'm saying let X stand for the number of heads in this. Number of heads in the outcome. Or number of heads in the sample point, whatever occurs. Okay. So for example, if I say that, what happens is that now you can see that every sample point is now turned into a number. Like here, look at this. This is a sample point, right? Sample point means what? An outcome of the experiment. That's called a sample point. Now this sample point is associated with a number. You can see that the number of heads in this sample point is 3. Okay. So it has become the number 3. Can you see that? How about the next one? This has got a number. This has got a number. The number associated with that is 2, right? So every sample point has become a number. So this is the advantage that you have. This sample point has the number 2 because it has got 2 heads in it. How about this? This has got 1 head in it. So everything has become a number, right? That means what are the possible numbers that you can have the sample points associated with? Like here, I've got the number 2. Here I've got the number, 1, right? And here I've got the number 2. And here I've got, what is the number here? 0. Okay, so every sample point has become a number. Okay, so what is the range of these numbers? Minimum I have 0, maximum I have 3. So your random variable seems to be taking only 3 values. So your X is taking only 3 values. What are they? They are nothing but 0, 1, 2. Okay, so only these values it is taking. But you know what? Every number signifies an outcome. No? There is an outcome or a sample point associated with it. For example, when X is 0, there is only one sample point that we can think of, which is TTT. But when X takes the value 1, I know number of heads is 1, but there are how many sample points are here? I think I made a mistake here. It is actually 1. 1 head only, no, in this. In this, there is only 1. So 1, 1, 1. There are 3 sample points which seem to get 1 associated with them, right? HT, H, and I'm sorry, one head, right? So I need to permute this head. Yeah. HT, T seems to have, and TTH. So these are the sample points associated with 1. What are the things associated with 2? 2 heads, right? So it can be HHT, HTH, or THH. So these are the ones. And for 3, of course, I have only one possibility, only one sample point associated with it. So now I come to know the meaning of these numbers. So random variable takes numbers, right? But actually they're depicting what? A single or a group of sample points. That means your entire sample space has become associated with numbers. And so it is a very huge advantage in many experiments where the number of outcomes is large. Okay, if the number of outcomes is large, what we can do is by introducing a random variable, we can group the sample points in various groups. Okay, depending on the number that they get associated with. So the study of them becomes more elegant. So this is the advantage of introducing a random variable and then studying the distribution. All right, what is the probability for these sample points? I see only one sample point associated with this value. So its probability is 1/8. When x takes the value 1, it corresponds to 3 sample points. So its probability is 3/8. And this is again 3, so 3/8. And this is 1, and therefore it's 1/8. So if the manner in which you have found the range for your x and the manner in which you associate some sample points with these numbers is correct, then you will get the correct probabilities found and they will add up to 1. Okay, this is the important aspect of any probability distribution. So why is it called a distribution? Because I had the total probability to be 1 and I'm allocating it to various things. I'm distributing it to various values, right? That's why it's called a distribution. Like you have one sweet and you're distributing it to many people, right? So that means there's one full thing which I have, one laddu which I have, I'm distributing it to various events, right? That's why it's called a distribution. Okay, that's hence the name. It's called probability distribution. I'm distributing one probability which I'm given to various events. So it's called a probability distribution. And what about the mean of the random variable? Who remembers? How do I find out mean of x? What is the formula for it?
X into PA.
Very good. Value taken by the random variable into corresponding probability. Remember, this is the formula for mean of x. How does it work? It is not, the mean of x is not simply, mean of x is not 0 plus 1 plus 2 plus 3 divided by 4. Usually what is the mean? Sum of the values divided by number of observations. All of you know that, right? That is the average, right? But that's not the way expectation of x is calculated, because the probabilities associated with these numbers, they act as weights. They act as weights. So I'm actually dividing by the sum of the weights, but the sum of the weights is 1 in this case. Okay, this actual formula is this for the mean. I think all of you know this formula already. Sigma xi fi by sigma fi. Does it sound familiar? Yeah, you had it in the 10th standard, remember?
That is it.
Yeah, here instead of FIs, you seem to have PIs. That's it. Okay, but sigma PI is 1 more, so that's why we are left with only the numerator. Okay, let us calculate it for this particular random variable. Random variable takes the value 0 and its corresponding probability is 1/8. Random variable takes the value 1, corresponding probability is 3/8. 2 into 3/8 plus 3 into 1/8. Add up all these, you seem to get the mean of the random variable. So 3/8 plus 6/8 plus 3/8. So the total seems to be 12/8. So don't be wondering why the mean had gone beyond 1. There is no restriction. There is no range there. The mean can be anything. Okay. Probabilities have got to be individually less than 1. and some of their probability should be 1. Okay, there is no going back on that. But mean can be any number. It can be a number more than 1 also, that we don't mind. So this is how we find the probability. But sometimes they give you challenging problems in probability distribution. So you need to practice a lot in probability distribution, depending upon how the balls are drawn. They may give you some bags and some balls may be drawn. They will say, find the probability distribution of number of red balls if the balls are drawn simultaneously, if the balls are drawn 1 by 1 without replacement, if the balls are drawn 1 by 1 with replacement. Okay, all these cases will be there. In all the cases, you should, you want me to do problems like that, or you can manage? Are you okay with those concepts? Or you want me to do and show you how the probability distribution can vary depending upon the manner in which the items are drawn? Are you clear about that, or would you like me to illustrate? We are okay with that, we can start doing a paper. What do you say? Okay, so we'll cross the bridge when it comes. This test I gave the last year batch. Okay, let's see if you are able to do it. An exclusive test on probability. First one is simple. Can you all attempt it yourself? Which theorem are you using? Someone else done already?
The answer 1 by 5.
1 by?
1 by 5.
Okay, Nishant got 1 by 5. Let's check. I hope all of you are using that universal theorem. What is it? A union B. On that. P of A plus P of B minus P of A intersection B. But what did it tell you? It has got corollaries, no? Depending upon the condition given. Here it's given to be independent, no? So we got to make use of that. So where can we use the independence concept? Only in the last term, right? So I can write the last term as P of A into P of B. I think we are given everything.
Said 1 by 5.
1 by 4. Okay, so you've given 2 different answers. Let's check. So P of A union B
1
is
by
3.
5.
Yeah, Vinay got 1 by 5. Okay. So half plus P minus half into P. Okay. Let me bring half this side. What is P minus half P? From 1 chocolate, I've taken half the chocolate. So
1 by 5.
So take 10 as LCM, cross multiply. 6 minus 5 is 1 by 10. Yeah, it's so simple. I don't know how one can make numerical errors there. 1 by 5 is. How many of you got this? Let me see. Without making mistake. Yeah. So remember, every exam is a battle, right? It involves many skills. Of course, warriors will be very brave, but and they'll be skilled also. But how bravely they encounter the enemies, that's very important, no? So your confidence, that's what is going to play a role. Look at the next one. A flashlight has 8 batteries, out of which 3 are dead. If 2 batteries are selected without replacement and tested, the probability that both are dead. Okay, let us write the structure. 8 are there. 3 are dead. Other are 5 are working. Okay, 5 are working. 2 batteries are selected without replacement. Okay, he has given you a hint based on what you should find the probability without replacement. That one. Tell me, Vinay, what's your idea?
Ma'am, I got, okay, ideas. You can use combination.
Good job. Good job. I like this answer. Without replacement means combination. Okay. Always remember, of course, some students get confused. They say, when I draw items simultaneously without replacement, and when I draw one by one without replacement, in both the cases, can I use combination? Yes. Yes, for probability. Okay. Of course, both experiments are different. We all know that the sample space will be different for both. But when you're drawing any number of items simultaneously without replacement or one by one without replacement, what should you use? What should you use? You should use combinations. Okay. So what is the probability of finding
A,
both
ma'am.
dead?
A.
Got A. Let's test. 3C2 by 8C2. Did you all get this? 3C2 by 8C2. Hope you remember how to calculate combinations. Hope you remember 3C2 means what? 3 multiples of 3 divided by 2 factorial. 8C2 means 8 into 7 by 2 factorial. Okay. So 3 by 28. That's what you said? Is there an answer like that?
Yes, ma'am.
Yeah, which one? A.
A.
I'm able to see. Okay. Is it clear for you? Yeah. Should I zoom or okay? A speaks truth in 75% of the cases and B speaks truth in 80% of the cases. Probability that they contradict each other in a statement. Okay, let us jot down first. Probability that A speaks truth is 75 by 100. Always when some data is given, if we jot down, we'll have clarity. Okay, so let us make out what he's trying to say. And probability that they contradict each other. That's what they want. So I've jotted down whatever he has given. I've also made out what he wants us to do. Okay, after that, when does a contradiction arise? For example, somebody visits your home and your father says, my child is very brilliant. Okay, and your mother says, no, he is very dull. Okay, that's the contradiction. Contradiction means one says, because statements are having a truth value, right? Either they are true or false. But if somebody is authentically saying something to be true, the other one is saying it to be false, that's where the contradiction arises, right? So here, when will the contradiction arise? Suppose A speaks the truth. Okay, your father speaks the truth and mother speaks the what? Lie. Okay. No, her expectations are at a very high level. So she says, you are dull. Okay, but it's all in your interest only. Or suppose father is actually lying and mother is speaking the truth. Okay, that may be the possibility, right? That's when contradictions arise, right? Okay, so tell me, these are mutually exclusive, right? These situations are mutually exclusive. So when the first one occurs, the second one can't occur. So they are mutually exclusive. The union will become plus, right? Union will become plus. And they're independent also. See, mother is not dependent on father while speaking. They're not influenced by what the others are saying. So they can be taken to be independent. So it's a concept of independence that they're testing actually. So it's a probability of A speaking the truth into the probability of B speaking a lie, and union will become plus probability of A lying and into the probability of B speaking the truth. Okay, can you fill these and find out? Of course, we can make out the probability of A line is 25 by 100.
It's 7 by 20.
What did you get, Nisha?
7 by 20.
7 by 20 you got. Anyway, it's one of the options, but let's see what others have got to say. You have to be quick and accurate in your calculations. That will matter in the exam. It will
7
matter
by
in
20.
the exam. What did you get up now?
7 by 20.
Oh, okay, then it must be right. Oh, got it? Okay. 80 by 100. I don't know how you all simplified. Maybe I can get 150, 1,500 plus 2,000. 35 by 3,500 by 10,000. Yeah, correct. Next one. A bag contains 2 white, 3 black balls. Okay, let us. Bag X contains 2 white, 3 black. Simultaneously, we should jot down. Okay, Y contains 4 white and 2 black. See, many students, when they come across a problem, they stare, they stare at the problem and they waste a lot of time. To start immediately, start action. Okay, one bag is selected at random and a ball is drawn from it. Probability of the chosen ball to be white. I know. See, this is the situation I was talking to you about. White is a part of both the bags X and Y, right? So which theorem will come into play? Let me see who is brilliant. Which theorem will come into effect in this? Which will be effective?
Total probability.
Probability.
Very good. Because white has got something to do with both the bags. Okay. So it is P of B1 into P of white from B1. This was what I was telling you about. They're asking you something which is actually inside 2 sets, which are actually spanning the samples. So that's exactly what is happening. So can you tell me these probabilities? What is the probability of bag 1? 1 by 2. What is the probability of white from bag 1? Very good. 2 by 5. Plus probability of B2 half. What is the probability of white from B2? It is 4 by 6. Okay. So 1 by 5. Quickly do the calculations. Okay.
8 by 15.
Correct. 3 plus 10. 13 by 15. Isn't it? Is there a choice like that?
1 by 3, right?
1 by?
It's
Oh,
1
yeah,
by
1
3.
by 3. I'm sorry. 2 by 6. 1 by 3. So fortunately, they didn't give that option. Yeah. 8 by 50. Got it? No? Okay. Next one. There are 4 white and 3 black balls in a box. 4 white, 3 black in a box. In another bag, there are 3 white and 4 black. An unbiased die is rolled. If it shows a number less than or equal to 3, then a ball is drawn from the second box, otherwise from the first box. If the ball drawn is black, then the probability that the ball was drawn from the first box. Okay. So we should go to the last sentence here. No? Which theorem, which probability is he talking about? The ball drawn is black. The ball drawn is black. Understood? The ball has been found to be black. What is the probability that it was drawn from B1? That's what he's asking. So, what do you think? What do you think will work?
Bayes' theorem.
Very good. Yeah, because he is talking about seemingly impossible conditional probability. looks like the probability, the difficulty can be is if I can find the reciprocal of this. Situations like this call for Bayes theorem. So Bayes theorem allows you to find the reciprocal of the events, probability of the reciprocal. Okay. So what will be the reciprocal of this? B given B1. Into, of course, it should be accompanied by B1, right? And in the denominator, we vary what is occurring after the slash. That is always the structure of Bayes theorem, right? So what will come in the next position? Instead of B1, I should vary it as B2 into P of. Okay, can you substitute all those and find out what is the probability of B1? He has given you a check there. The probability of B1 is not half, isn't it? What is it? If it is less than or equal to 3, then B2 will occur. Okay. So can someone tell me what is probability of B1? When a number more than 3 occurs, no? What are the numbers more than 3? 4, 5, 6. What is the probability of that? Half. Half only. Yeah, but he has given it as though it is very tricky. He could have changed it. Okay. Anyway, here they're both equally likely. Okay. Substitute. What is the probability of black from bag 1? Huh? Black, no? Black is 3 only, no?
3 by 7.
Huh? From bag 1. From bag 1, black. Am I right? 3 by 7. Okay. And what is the probability of bag 1? Half. Okay. And same things in the denominator. Plus, what is the probability of black from bag 2? This 4 by 7 into. Of course, these probabilities should be complementary. There are only 2 bags, right? No, these should be complementary. Okay, tell me after that. What's happening?
3 by 8.
3 by 7 by
Yeah.
what is the answer now?
3 by
Jessica? What did you get?
I'm getting 3 by 7.
3 by 7 only, right? Yeah, I'm also getting it. Let A and B be 2 even such that P of A is this, P of B is this, P of A union B is this. Okay, do this yourself. It seems to be a routine problem. From this, what we can make out, you find out. What plays a role? Just by looking at it, you know what is to be done. What should you make use of? Yeah. Use the addition theorem. Addition theorem works in many cases, and this is one of them. Okay, make out your P of A intersection B and tell me first. Let's not go wrong there. So what is it? This is 3 by 4. This is 3 by 8 plus 5 by 8. What did you get? 1 by 4. Correct. Okay. Okay, can you calculate this yourself just by making use of the idea of conditional probability, definition of conditional probability?
6 by 25.
6 by 25, that's what you're getting. Okay, that seems to be an option. Options B, no? Okay, what is P of A given B? That's nothing but P of A intersection B into P of B, correct? And P of A dash given B is P of A dash intersection B by P of B. Is there any way we can say that they are independent? Then we can make use of it. No, I'm tempted to use it, but they're not independent, obviously, because P of A intersection B is not P of A into P of B, right? So I can't use the independence, right? So let me substitute what I know. P of A intersection B has been found out. So let me substitute as 1 by 4. And what do you do for P of A dash intersection B? That's what I was training you for. What is A dash intersection B? Who remembers? The universal way of finding out. Outside A, inside B.
P of A intersection B.
P of B minus P of A intersection. Right? Divided by P of B square. Okay, substitute. P of B is 5 by 8. 5 by 8 minus 1 by 4. And P of B square. P of B square will be 25 by 64. No, computations can't be helped. 8, 5 minus 2. 3 by 8. Anna, how did you finish so fast? She's right. 6 by 20. No? That's smart, Anna. Very good. Seventh one. For two mutually exclusive events A and B, P of A is this much. P of A bar intersection B is this much. What is P of A slash A union B? Come on, do that. Okay, what is he asking? So let us prepare ourselves for that. P of A given A union B. Okay. This is nothing but P of A intersection A union B. Do you all agree? Huh? What is A slash X? It is P of A intersection X by P of X, right? Oh, I didn't mean the complement. I mean, it's a single event. That's what I meant. Can someone tell me what is the intersection of A with the A union B?
A.
Very good. Yeah. Because A union B contains A, right? A is a subset of A union B. So its intersection can only be itself. Yeah, we are actually considering the other meaning of the conditional probability. So what is it? Are you given P of A union B or not? What is P of A bar intersection B? Who remembers? A bar intersection B. Actually, P of A bar intersection B is nothing but P of B minus P of A intersection B, right? And P of A is 0.2. But if you add these two, what will you get? Vinay, if you add A with, because he answered so brilliantly before. Vinay, if I add A with A bar intersection B, what will I get, Vinay? If I unify these two, if I unify A with A bar intersection B, what will I get?
Ma'am, you will get
Yeah, you will
A
get
union B.
correct. You all understand that? That's what he is giving. Indirectly, that's what he is giving. So what will be the probability of A union B? It will be the sum of these probabilities. So he has given you in a platter, actually. P of A is nothing but 0.2. And P of A union B is the sum of these two. So 0.2 plus 0.3. That is 2 by 1. That's why you need to learn Venn diagram properly. You need to be, aware of the basics of Venn diagram. That's it. An unbiased die is tossed twice. What is the probability of getting 4 or 5 or 6 on the first toss and a 1, 2, 3, 4 on the second toss? Okay. Who can tell me this? Do you, first of all, realize that when you toss dice, you're dealing with independent events, right? See, you're tossing one die with your left hand and you're tossing another die with your right hand. in whatever manner you may be doing your experiment, or you may be tossing the dice with your same hand, but you're tossing them one after another, say. That's another possibility. You're tossing 2 dice one after the other with different hands, or you're tossing 2 dice simultaneously with both the hands. That is one possibility. Or tossing 1 die twice. All are same. But they are independent. No, suppose I get some number in the first experiment, that wouldn't influence what I get in the second trial. So they're independent trials basically. So what is the probability for you to get these numbers 4 or 5 or 6, 3 by 6? What is the probability for you to get these numbers 4 by 6? What should I get? What should I do to get what I want? I want these in the first toss and these in the second toss. I want these in the first toss. And what should I do? Multiply, because they are independent. Tell me what this is. Half into 2 by 3.
1 by 3.
1 by 3. That's it. Okay. It's 1 on 3. 1 on 3. Go to the next. Let X randomly selected from the set of odd numbers of the set. So X stands for 1, 3, 5, 7, right? From this set only, right? And Y is randomly selected from the set of even numbers. So 2, 4, 6, right? Z stands for X plus Y. Z is X plus Y. Probability that Z is the product of prime numbers, product of prime. Tell me, what are the possible values for Z? Z stands for X plus Y, right? It's a new variable depicting some of these. Therefore, I can have 1 plus 2, that is 3. Okay. I'm just thinking of all possibilities. X plus Y, right? And this 3 is, of course, product of, is it product of primes? Is 3 a product of prime? No. Okay, so what is the other possibility? Z can also be? Z can also be this, that can also be this, right? 1 plus 2 is 3, or it can be 1 plus 4, 5, it can be 1 plus 4, 7. But these being prime, they can't be product of primes, right? Okay, then what are the other possibilities? 3 into 2 is a possibility, right? So shall we just pick the possibilities? When Z is such that it's product of primes, when can that happen, product of primes? When I have 3 into 2, that's a possibility, right? 3 into 2 is a possibility. That's all I think. Then probably 5 into 2 is a possibility. But it should be some of those two, right? It's a condition. Possible values taken by Z are 3, 5, 7, and then next set of possibilities 5, 7, and then 9. Next set of possibilities with 7, 9, 11. Next set of possibilities 7 plus 2, 9, 7 plus 4, 11, 7 plus 6, 13. Out of these, I think we have to rule out all the primes, right? Primes are not expressible as product of primes. So these are out of the scene, right? 7 also, 11 also, 13 also. So what are the possibilities? Z can be 9 or Z can be I think 6 arose somewhere, right? 6 is not a possibility. So only 9 is possibility, right? 9 is expressible as 3 into 3. But 9 occurs in how many cases? That is x plus y. So 7 plus 2, or it can be 5 plus 4. There are 2 possibilities. And both these, in both these cases, it's expressible as. So there are 2 cases in which it is expressible as this. And what is the total, by the way? Huh? Huh? 3 cases. In 3 cases. What are the 3 cases? 3, 6, 4, 5. 3, 6, 5, 4, 7, 2. Oh, all right. Why did I leave it? Yeah, of course. I see. Yeah, 3 cases. And what is the total number of cases? 4 into 3, 12, right? 1 by. Of course, we analyzed. Of course, we could have made out that only 9 is the possibility. Okay, next one. A bag contains 5 red, 3 blue. 3 balls are drawn without replacement. The probability of getting exactly 1 red. What did I tell you? What did I tell you? Whenever they use the terminology without replacement, then what should you do? Combination. Yeah. Can you work out? Exactly 1 red. What did you get? 1 red ball can be chosen in 5C1 ways. And blue balls, the remaining 2 should be blue necessarily. So 3C2 divided by 8C3. Okay. Tell me what it simplifies to.
So it's 15 by 56.
Very good. Correct, Nishan. Just now I finished calculating. 5C1 is nothing but 5. All of you know. 3C2 is nothing but 3C1, which is 3. And 8C3 is nothing but 876 by 3 factorial. Okay. So 6 and 6 will get cancelled. 56. So 15 by 56. Yeah, option is there. Okay. So then we have assertion and reasoning. We are running out of time. So let's see. We can do some section B. Yeah, I just wanted to test whether you can do this type. A card from a pack of 52 cards is lost. From the remaining cards of the pack, 2 cards are drawn and are found to be both diamonds. Find the probability that the lost card was a diamond. We'll do 19 and 20, okay, and test whether you have understood. A card from a pack of 52 cards is lost. From the remaining cards, 2 cards are drawn and are found to be both diamonds. Okay. So let us find out what he wants. We want. What happened first? What happened first? The two cards are drawn and are found to be diamonds. So we got two diamonds. This occurred first. So we should put it after the slash. What is the probability? What is the probability that the card lost was a diamond? So the success lies in figuring out what he wants us to find. So we got two diamonds. What is the probability that for us to lose a diamond? So we got two diamonds that happened first. So I put it after the slash. I hope you have understood. In simple language only I'm telling you, okay, so that it be easy for you. So tell me whether it is simple conditional probability or Bayesian.
Bayesian.
Huh? Bayesian, very good, because this is seemingly impossible conditional probability. So this will be addressed like this. I got two diamonds after losing two diamonds. Okay. And for that, I must have lost, was it one card or two cards? Only one card, no? One card was lost, yeah. Lost a diamond. Divided by, same thing, no? I got two diamonds and I lost a diamond. Into the probability of the diamond. Plus, who's going to tell me what is the change that we bring in here? What is the second possibility? What do we change here? We retain the numerator. Did you know that in Bayes' theorem, we always retain the numerator. We change the denominator only, okay, giving the other possibility. What is the other possibility? Tell me. What is the other possibility? If you didn't lose a diamond, what you would have lost?
Other cards.
Yeah. You would have lost a non-diamond. Understood? Lost a non-diamond. Into probability of losing a non-diamond. See, many students tell me that they use E1, E2, and then A given E1, E1 given A. But if you write like this, it will be easier for you. That's what I feel. Okay. If you go to the last step and if you write what is the condition probability that you want to arrive at, right? It's reciprocal. That's when Bayes' theorem works and everything goes very smooth. Okay, now you tell me, first of all, I think these are simple to find out. So let's find out what is the probability of losing a diamond. What is the probability for us to lose a diamond? There is a pack. Okay, initially there is a pack. Nothing was done to it. The pack is intact. What is the probability for me to lose a diamond in it? How many diamonds are there? 30. So 13C1. 552C2. That is the probability of losing a diamond, right? Okay. And after having lost a diamond, this is a different situation. For this, in this scenario, what happens is that the number of diamond cards would have become 12, right? The new pack. The scenario after losing a diamond. Number of diamonds would have become 12 and non-diamonds would have become non-diamonds? Same, very good. Yeah, 39. But total cards will be 51. Remember that. Because you lost a diamond. Okay. So what is the probability for you to get two diamond in this pack? In this new pack. After losing a diamond, this is your new pack, right? In this new pack, what is the probability for you to get two diamonds? Where are the diamonds? Diamonds are here. Okay. Okay. What is the probability for you to get 2 diamonds in this? 12C2, you are drawing 2 diamonds, right? So 12C2 divided by, who's going to say? 12C2 by, how many are there in the pack?
51.
51 C2.
Eight.
Copy paste that. Same thing will come here also. Losing a non-diamond. Next scenario. What is the probability for you to lose a non-diamond? How many non-diamond cards are there? How many non-diamond cards are there? 39, no? So probability for you to lose a non-diamond is 39C1 by 52C1. The fresh pack, when you didn't lose anything, the probability for you to lose a non-diamond. Okay, now tell me the new contents of the pack. When you lose a non-diamond, how many diamonds will remain? Very good. All the diamonds will be intact. How many non-diamonds will be there? Very good. 38. Okay. So in this scenario, what is the probability for you to get 2 diamonds in this pack? In this new pack? 2 diamonds. 13C2 by, very good, 51C2. Yeah, because the number is total is anyway 31. No. Understood? Okay, now let's cancel whatever is possible for us to cancel. Okay, we can cancel all these. Cancel this. I think we can cancel this also because it's found everywhere. Cancel only if it's found in all the 3. Okay. I think we can cancel this 13 also. It's occurring here, it's occurring here, it's occurring here. Okay. So what is left behind? 12C2 by 12C2. Can you calculate this alone? Don't be struggling by, calculating all the denominators. That will be unnecessary. What did you get? 12C2 is what? 12C2 will be 12 into 11 by 2. Okay. 12 into 11 by 2. What will be 13C2? 13 into 12 by 2. That is nothing but 78. 78 into. Did you calculate? No? What is it? 66 by 66 plus 234. Am I right? 66 by. Is it right? That's what I seem to get. 11 by 50. How many of you got 11 by 50? Can you let me know? Oh. Yeah. 11 by 50 is correct. Yes, Sachin. Hope you're comfortable with the calculations. So actually, I think you have reached a stage where you can intuitively find out whether it is a mere conditional probability or Bayes theorem is called for. So you have to distinguish between those situations. Next one, a bag contains 4 balls. Two balls are drawn at random without replacement and are found to be white. What is the probability that all the balls in the bag are white? I think it's a bit not complicated. It's a bit different. So it seems there are 4 balls and we have drawn 2 balls and we found them to be white, right? 2 white balls occurred. What is this problem is slightly different. What is the probability that all the balls in the bag are white? That means, how many balls are there? 4 whites. 4 whites are there. That's what he's asking in the bag. We got 2 white. When we drew balls, we got 2 white. But he is wanting the probability that the bag already has 4 whites in it. Okay, so what do you think? Is it simple conditional probability or is he talking about seemingly impossible conditional probability? What do you think? What's your take? But there are various possibilities. It could have been 4 white, it could have been 3 white, it could have been 2 white. There are many situations. I mean, in the sense, this is entangled in the same situation. B1, B2, B3, and your A is entangled there. So that situation, I don't think it is simple conditional probability because the situation, becomes less complex. If I think of the reciprocal, I got 2 white when there are 4 whites in the bag and the probability for it to be having 4 white. Probability bag has 4 white. Okay, divided by. Can you tell me how would you alter the denominator now? Initially, what did we think? We assumed that the bag had 4 whites. No, what are the other possibilities? What are the other cases?
It has 3 whites.
It has got 3 whites, or it can have
2 whites.
2 whites. Can it have 1 white?
No.
That's impossible. Because when it has only 1 white, we couldn't have got 2 whites in the first place. So that is seemingly impossible. So we'll not consider that case. So we'll replicate what is there in the numerator. I got 2 white when 4 whites are there in the bag. Okay. Into probability for 4 whites to be there in the bag. Okay. Then what can you say? I got 2 white when there were 3 whites in the bag into probability of 3 whites in bag plus I got 2 white when there were 2 whites in the bag into probability of 2 white in the bag. These are the exhaustive cases. No, I don't think there is any other possibility. But I think only Bayes theorem works in this case. So it's not mere conditional probability that we can, arrive at intuitively. Can you just tell me quickly what are these probabilities? What is the probability for you to get 2 white when there are 4 whites? How many are you drawing?
1.
How many are drawn? 2. Okay, how many are there totally? 4 whites are there. So what is the probability for you to get 2 white when there are 4 whites? There are 4 whites. Okay. What is the probability for you to get 2 whites out of it? The bag has only 4 whites. Okay. What is the you're drawing 2 at random? What is the probability for it to be 2 white? That's what I'm
1 by 2.
1, isn't it? You will definitely get 2 whites, irrespective of what you get. It's a definite probability.
Yes, sorry.
What follows that? That's what is important. I'm curious to know, what is this probability? What is the probability for the bag to have 4 white? It can have 4 white, or it can have 3 white, or it can have 2 whites. All these possibilities are there. What is the probability of these events? He has not mentioned all these. In other words, I'm asking, what are these probabilities? What is the probability for it to have 2 whites or 3 whites or 4 whites?
Is it 1 by 4 factorial?
Very 1 by
4 factorial.
why, ma? The bag has 4 whites or 3 whites or 2 whites. Only 3 possibilities. No, 3 cases, 3 distinct cases arise. What is the probability for these to happen?
1 by 3.
1 by 3. Simple. Yeah, it's 1 by 3. Let's not complicate things. Okay, all the events are equally likely. So unless and until mentioned, it's 1 by 3. All the events are equally likely. For it to have 4 whites, or for it to have 3 white, or for it to have 2 whites, we have no clue at all. So we'll assume that these are all equally likely. So what is the probability for it to get 2 white when there are 3 whites there? Tell me. This is an important aspect. I got 2 white, but there are 3 whites and some other color ball there. So what is the probability for me to get 2 whites in that case? There are 3 whites and some other color. Okay, so I don't want that color. I want only 3 whites. So the possibility for that is 3C2 by 4C2. Right? Into 1 by 3, of course. And the last one, I got last one. I got 2 white, but there are 2 whites in the bag, right? So 2C2 by 4C2. I don't want the other color ball to come. Okay, I want both the balls to be white only. So 2C2 by 4C2 into 1 by 3. How many of you understood this problem? Raise your hand. The logic. Yeah, Panna understood. Okay. Others, if you have not followed, can you let me know where you did not follow? Understood, right?
I mean, probability of getting 2 white out of 3 white.
2 white out of the 3 white. Okay. So that means your bag will be like this. Your bag will have 3 white and say 1 red. Okay. You are taking how many out of this, Shah? How many balls are taken? 2, right? So you are taking 2 out of this. But you want these 2 to be what? White only, right? You want these 2 to be white. But white will occur from where? From this collection only, no? So that is 3C2. But what is the total possibility? 4C2. Understood, Shah?
Yes, got it.
3 whites and some other ball. That is that case. And this case is, of course, simple to understand. Again, same logic, right? This one. This one, I've got 2 white. I've got 2 white and some other color, maybe red. Okay. So total possibility is 4C2. And white can occur only from white. That's our understanding. Okay, so 2C2. The whites have to occur from this only. There's only one combination, 2C2. One combination in which 2 white balls can occur. So 1 by 6. That's the possibility. Understood? Because the balls are distinguishable, that is, assumed. So we need to. So I suppose you can complete this paper. I'll send this paper with solutions. Okay. And let's see if we can complete it by today. So tomorrow I'll give you a break and probably we can meet on Saturday. By Saturday, what can you complete? Let's have some meaningful and realistic goals. Maybe first 4 topics and vectors can you complete? 4 topics and vectors. And that's what I'm saying. Relations and functions, inverse trigonometry, and matrices and determinants, and vectors. Can you complete by Saturday? I think this will be okay. No, vectors, not much actually, but you have to thoroughly finish. Okay. And then in the next set of revision, we can have whole of differentiation and application. That can be one particular unit. Then we can have the whole of integration. This on Saturday. And we can have this on Sunday. Sunday, is it possible for you to come? No? Whole of Sunday you can complete. I'll just test you in this, and Monday we can have this completed. And this one will be applications and differential equations. Applications, differential equations. And then the next unit can be LPP and others. LPP, probability, 3D, vectors, again I'll test it. This can be one unit. This I can test you on Monday, Wednesday. And Thursday we'll do papers. So can you complete by Saturday, first 4 and vectors? Again, I'll include vectors later. That will be a good way of revising, I thought. I think we have covered everything, right? Okay, so let's meet on Saturday. So because I'm giving you 5 topics, so try and complete probability today itself. Okay, do the worksheet which I had given, and complete your textbook problems, worked out problems, and miscellaneous problems, examples before the miscellaneous, everything. Okay, and try and complete these by Saturday evening. I'll let you know when we can meet. Maybe 5 o'clock, 5 to 8 also we can have. And we'll revise all the concepts and we'll do a paper on all these topics. So that will finish our revision on these. And after that, differentiation application is a saga, right? So you need to spend some time. One day will be sufficient, I think. So let's hope. And then we'll take it forward. Okay. So let's meet on Saturday and you come thoroughly prepared. Okay. With all the topics that I specified. Then it will be a good revision.